Welcome everyone. So thank you for coming today. My name is Carlos Rivera. I work in DHI Germany in Berlin. So today we're going to talk about complex geological modeling for groundwater models. And I will try to focus the presentation basically in our latest development for 3D and structure meshes. So what is now being published in the last release in November. If we have some time, I will even show a few things in what we are currently working and what is going to come in the release later in April this year. So the whole idea is to keep the presentation, the PowerPoint part condensed so that we have more time for the live demonstration. I have prepared two examples, so one using geological data coming from external software and one with the data has been basically prepared with standard tools in Python. So we can look this. So I would like to start with some announcements or do a quick introduction. Then what is it about when we say 3D meshings? So what are the new features that we have in the super mesh processing and live demonstration? So in case you don't know, so we have a new free self-paced course is related to the topic of the presentation. It's called Advanced Modeling of Complex Geologies. In this example, what we are doing is we are trying to demonstrate the entire workflow with real data from Western Australia using the 3D geological model of the Gilgran Official Musgrave region. Maybe you are from the region and you know the data, so you can enroll. You will get a copy of this presentation later per email the next days, and you will see the hyperlinks here and you can directly go to the landing page and enroll. Together with this presentation and with a number of activities, I would like to mention that DHI is running a dedicated campaign called FEFLOW Advanced Features. So this is the module which allows you to access to the technology that I'm going to present today. For a limited time, we are providing 50% for upgrade. So this module is offered for a specific license type, which will be discussed later. So for those who are really totally new to FEFLOW, so FEFLOW is a software for groundwater flow, contaminant transport, groundwater age, and heat transport under variable and saturated conditions. So we have been doing this groundwater business since already a number of years. So FEFLOW exists in the late 70s, and since then has been always being as an all-in-one groundwater solution. So we customize our interface in a way that we can support flow, mass transport, and heat transport. We keep developing the software in such a way that we have 2 releases per year. These releases are oriented in saving time and boost efficiency with different workflows, from Python programming interface to the methods that I'm going to show today about meshes and model conceptualizations. And we also have a lot of attention in what is visualization in 2D and 3D. So I wouldn't say much more about these slides for FEFLOW because we want to concentrate to the 3D meshes. So FEFLOW will help you with in the whole model conceptualization, mesh design, setting, simulation, calibration with PES, PES++, prediction, uncertainty analysis, so that you have the whole workflow within the same software. So now to the topic of this presentation, 3D meshes in FEFLOW. So you might have seen this slide so many times in my previous webinars. It's a good one to show the overview of different workflows. So we have possibilities to create meshes from 2D, where you create a triangular mesh using triangle or advancing front, extrude the model, and then you can end up with a layer-based model with a 3D and structure model. But what we are going to discuss today is basically the workflow below this 3D super mesh. 3D super mesh means that you prepare the data in a way that represents the 3D concept. So your geology, your different faults, surfaces, horizon, this data is 3D available. And we use this data to build this representation of the concept called super mesh, and we create an structure mesh out of this. So, but what is this 3D super mesh? It's a set of different geometrical informations in 2D or 3D, depending on the case. Could be lines, if we want to simulate drainages, pipes, barriers, points for wells, surfaces in the case of 3D geometries, where we want to simulate inclined faults, geological contacts, and others. So all of this is part of the super mesh, and will be acknowledged during the time of meshing in FEFLOW, either in 2D or in 3D with TechGen. So that's a very simple example that we will look at it later about a 3D super mesh. So you can, let me put my pointer here. If you see the different geological contacts, internal contacts, there are some points, maybe these are wells or any other information. So we try to represent all this information coming from a geological software. So recently, so last year, we introduced concept of material lookup tables. So we want to go more and more in the direction of material conceptualization in 2D and 3D meshes. So now you have even the possibility when you build your 3D super mesh to define information about a region, let's say sandstone, and this material can be linked to multiple parameters like conductivity, porosity, storativity, parameters for the mass transport, for the heat transport, and so on. For those, because I see a lot of people here with some Python skills of this information is also available through our open programming interface, so you can access and ask FEFLOW, give me information about what is sandstone, and then give me the parameters, and you can interact in this way. It's quite practical because if you start always with the same definitions of materials for different projects and different locations, you can always reuse this kind of database. Okay, so back to the topic of meshing. So what are the possibilities that we have in FEFLOW, or what we were suggesting in the last years until the last release? So what is possible? I mean, you can always go for layer-based models or with prismatic elements because these are easy to build, they are easy to maintain. If you have specific information regarding to some locations of the model where you would like to adjust, maybe you have an underground tunnel or a subway or a pipe system, so you can use the workflows, existing workflows to create tetrahedral meshes and only touch those parts of the model which are interesting. If you have a geological model where there are a lot of pinchings or different intersection between faults and geological content, so we can also use this workflow. These three first points are used in the layer configurator. This means that we start from a 2D mesh, 3D mesh, and then at some point you decide that you want to make the model partially or fully unstructured. Today's webinar is going to focus on this, in when we have a structural model, some 3D information, and we would like to basically create a fully tetrahedral mesh. So this starts from a 3D super mesh representation, which is a set of different geometrical information, surfaces, points, and edges. We have the possibilities to store this information through the different workflows, and we actually recommend you that you do that because FEFLOW is going to activate different what we call super mesh groups and then store data related to the regions, to the node selections, to the phases, and etc. So when you generate a mesh with TechGen for the tetrahedral mesh, FEFLOW is going to report and give you all these different geometries that you initially define as relevant for your workflow. These are a number of file formats that we support. There are a few more that I didn't put it here because these are the most common. So on the left side, you see geological models. So many people work with these geological models. So 3D GeoModeler from Intrepid in Australia, GoCat, we support M files, so TS files, Leak from Mesh files, LFM, and MikeSign is also capable to export in DXF, which is also readable by FEFLOW. So I received recently a lot of comments say, hey, what is if I do not have a geological model? So how can I use these FEFLOW advanced tools? So I would like to emphasize this. So you are not really forced to use these geological models. You can build your information directly using standard file formats like 3D shed files, Autodesk, AutoCAD, KeepWare, BTUs, BTP files, object files, and STL files are very easy to use. I'm going to show you a workflow with Python where you can create faults or surfaces in STS files. And this can be binary access, so you can really easily script them. And of course, we support meshing files coming from TechGen, from the mesh generator or from triangle.mesh. So the whole idea of this workflow is if you have data, if you have a geological model, or you have a 3D representation of something, so you want to take the maximum advantage of this. And to do that, so we want to migrate as much as possible into our groundwater model. So if we start with some geological interfaces, so we will be able to represent it through the meshes and then create tetrahedral meshes. And from that point, so we can build a fully unstructured mesh. Sounds simple, but it's not simple. So those of you who have been already working in these 3D meshes, so you know very well this definition of this piecewise linear complex. So behind the scenes for now, what we are using is TechGen, is the mesh generator from the Bias Institute in Berlin. So the simple explanation of a PLC is that all your data, all your geometrical information has to fit in a proper way. So if you have, in terms of geological horizon or faults, so these are triangulated surfaces, so they need to fit very well. Let me put the laser here. So if you have intersection between a line, this could be a tunnel that you are simulating as a 1D in FEFLOW and a fault, this has to be also triangulated here. Or you have a horizon and a fault, then the intersecting line needs to be present in the triangulation. If no, this will be reported as an error, and this error is called self-intersection. And this was basically the major limitation in the workflows in a number of years. So how this self-intersection happens, from my experience, comes because these geological softwares triangulate some part of the information in one way and the other part is different. So they might triangulate cores, the horizons, and the faults very, very fine. And obviously they do not fit. So if you zoom, then you will see here the triangulation is not fitting in these cases. So these are simple examples where it fits. So it's a nice, but we know the geology is complex. So we want to achieve higher levels of complexity. That's another example. Here is a simple 3D layer. So you also, one typical situation which we observe quite a lot is that the input triangulation coming from the geological software is sometimes overemphasizes or unnecessarily. So you see all these triangles. They are going to perturb my final finite element model in FEFLOW. So this is something that you need to take care in the software outside or use now today our new tools. And this is a clip of both the left geological model and right the FEFLOW model. So the representation of the contact is properly done, but I would say maybe the interface of the transition is probably the refinement is too small. So we are ending up with a lot of tetrahedrals due to this situation. So now let's talk about latest implementation. So we are looking now new ways of doing this or improving the workflows. And that was a long journey that we take. So we investigate in DHI different alternatives, solutions, and then we came to a very good point. So we meet these guys, GOD Solutions. They offer a very interesting technology associated to next generation of modeling challenges using advanced meshing. So they are really specializing in meshing. So a few examples is incremental surface-based modeling. So where you can introduce your different surfaces, update your conceptual model every time. So it's in a very smart manner, and it's something that it really happens in our hydrogeological cases because we never finish the conceptual model, always new data coming in, new interpretations. So they are also quite skills in what is 3D tetrahedral meshing and different workflows. So they do also a number of things, implicit modeling, explicit modeling, and so on. So if you like to know more about GOD Solutions, so you can please visit them and then get in touch with them. So what we are doing is, so we have a partnership with GOD Solutions, and we start working since the last year in a new workflow, what we call super mesh repairing, or it's actually called super mesh processing now. Which offer you a major benefit is to repair improper 3D data. So when we mint 3D data, I specifically am talking about surfaces and polylines. So we have tools now in FEFLOW to repair this improper data. In the same way that I was showing in the previous slides, so we have now the possibility to integrate new data sets, because every time that comes something new, we are capable to repair or remesh. So this is offered under a new module called FEFLOW Advanced module. This FEFLOW Advanced contain the access to GeoD capabilities, meshing capabilities, is offered for FEFLOW FM3 licenses and FMH3 licenses. So we want you to support in this migration. So that's where we are basically running this campaign that I mentioned at the beginning. So the workflow is very simple. So you start with any data that you have. It of course has to be an enclosed 3D domain. So you see here a number of faults intersecting outside the topography. So it's not going to work. So if I try to mesh in this with TechGen, it's going to report a self-intersection error. So what we do is we basically call a repair process, which is taking sure that every of these surfaces are intersecting properly, and we are able to create a tetrahedral mesh. And this obviously increments the chances that we create a 3D tetrahedral mesh in FEFLOW. So here you can see the different surfaces, which are cut in some geological models. Okay, but how it works, I try to explain. There are just two workflows, which can be really combined in different ways, how you want, depends on your data. I think you need to get started with this and realize. So one simple example, which was probably not even thought when we started implementing these first steps of super mesh repairing. But since we use it, and we have been also receiving quite some feedback in the last weeks from our users. So there is first workflow, which is called remesh workflow. Remesh means that you pass a surface. So I put as an example 1,716 vertices. So you can see probably in the screen the surface is not that well triangulated. Maybe comes from a geological software, maybe comes from GIS. So you can also create a thin surface in GIS, which will do some delunate triangulation, but maybe not that good as we need for FEFLOW. So you can use this super mesh remesh workflow to basically smooth your surface, so you can improve the quality of the surfaces. So you can go more and more refine the surfaces. So you can even go the other way around. So you can coarse the surfaces if there is too much information about this. Not required, so you can course it, and it's going to do kind of surface reconstruction based on the existing triangulation. We do some different differences here. So what is topological meaningful? So there is an option called sharp features. So you can call this remesh operation. I put here a cube because it's the most obvious case where you will see the effect of this active sharp feature option. So if you call sharp features remesh with sharp features option, what basically is doing is sending this set of faces from the cube to the algorithms, and maintaining the edges, preserving the location of the edges. If sharp features is disabled, so we see the whole thing as a surface, so there is no maybe enough information to really tell there is a cube and has to be preserved the 90 degrees angle between the faces. So this could be also very positive in the way that in cases where you do not really need to preserve, so you can smooth and then smooth your surfaces, so there are more chances to fix the problems, correct the triangulation issues and the intersection issues. The other workflow is called repair workflow. The repair workflow starts like this. So you have a domain which could be previously remeshed by the workflow that I was showing you before or not. So if you think the triangulation is good enough, so you can just start with what you have. from the beginning on, and then you can add a number of information. This information in this example is a fault, so a very simple plane calculated or created in Python. Then we call the repair, and the repair tool basically, it has a possibility to, it's optional, it's up to you. You could decide to discard parts of the surfaces that are outside the domain. So it has the possibility to cut the plane and then throw away what is not inside the box or the domains. And what it will do, it will basically here reconstruct the surfaces in a way that is acknowledging the intersection between this box or this domain and the plane. And now let me switch to my FEFLOW screen. So I have, because of the time, so I have prepared a few things already up front. So let me close this. So so that's my call base super mesh, so very simple. And I like to take simple things because it will help me to show you the workflow, and we don't need to wait a lot for the whole processing. So what you see here is so it's a domain, is the most simple. So this box you can create it outside if from FEFLOW. So you can use a geological software, or you can use any Python script. So I have here my view with PyCharm. So I use quite a lot PyCharm. So many people use Conda and others. So I could recommend you, if you don't have a geological software, try to use PyVistas, because quite nice. I have using for a number of years, and works with a lot of formats and data. So here I have a simple CSV file, but could be any that file where I have a set of points X, Y, Z. Maybe this information comes from topography. Maybe I have a digital elevation model. Maybe I have something in GIS, a raster. So I could use this data to create a surfaces already here, because we need to have surfaces to start with this workflow. So let me, it's not exactly the same surface that I have in the model, but it's probably, it does not really matter. So we can see here it's creating. So if you, here this is a surface of an open pit, so it's a specific mining level, so it creates a surface. So we can use this. So let me check this and then plot the points. And that's a start from that. So there's a cloud of points, and then we are using this cloud of points to triangulate. So that's the cheapest and simple way to create surfaces if you don't have a geological model. In case you want to get a copy of the script, let me know. I have my email. I will put my email address at the end of the presentation. I can share it. So it's quite simple. So that's the way how this surface was created. How you create the other sizes of the box. This is something that I explain in the self-paced course. So I use basically a lot of SMesh files coming from TechGen, because these are quite simple to script. So this, so you can see the triangulation is quite good, but let me try a few things so to demonstrate. So I'm gonna, here I have my super mesh processing panel, 2 sections. So the first one is related to the repair. The second is related to the retriangulation surfaces. I'm going to start with the second one. I want to say to GOD that I would like to remesh, preserving the original vertices. So that is what I was referring before as chart features. And 0 default means that we have a method in FEFLOW to calculate what is the average size of the little polygons that we have, and then we use this as a target element for the discretizations. Sometimes you don't know what is a good target, so I would recommend you to just leave it run, and then FEFLOW is gonna plot here the information. I will recommend you also, so if you, so there is the possibility to go to the FEFLOW global settings, so you can dump these surfaces. So there is a specific format of GOD. So they also have some Python bindings, which are quite cool. I use it for a while already, and you can also read this data outside Otherwise, you can also dump it in BPT or BTM. So So you don't need to remesh every time or repair. So you can have it outside, and then the next time you can just import it in FEFLOW. It will save some time. So the triangle here means remesh, and it's gonna take few seconds. Is probably already done. Yeah, it's already done. So it's now, I get some inputs about number of blocks. So it's just one cube. All this information is optional. You can activate or deactivate. And then the number of surfaces and the number of vertices. So it's, now if you can hear, my PC is doing something, and it's gonna take probably another few seconds more. It's and here 250 is what I'm using this information. So we are also dumping for debugging purposes, and also maybe for you to document. All this information is created in a folder at the same level of the super mesh, so where you can see the settings, so you can always remember what has been used. So now you see the triangulation is done. So we have discretized it, definitely a bit better than before. So what I'm gonna do now is to introduce some data. I was reading in between some questions about leapfrog in the chat. So I will highly recommend you, if you work with geological software, try to export your data in different subsets. So if you have geological contacts, so you export it separately, don't export everything as one, because we have the ability to do all these processes stepwise, so that you could basically identify where is the potential bottleneck in your workflow. So I import the number of faults, and these faults were created also with PyVistas. And what I was referring before to integrate the data easily is that you can add it a number of times. So I'm doing one by one this, and the next minutes I'm going to show you what is the future of FEFLOW with this. So we have a different workflow to improve all this, which is really, really practical, in my opinion. So I have done, and that you see well, also I have exaggerated the heights. So it's really, so the thing is not fitting at all. And so what I'm going to do now is to say this time I would like to repair. For repair, we go to the first part, to the upper block. You have a number of options. Simplify repair output means that GeoD is gonna add additional triangles to the original surfaces because of the repair process. After it's done, it's going to remove the extra. Surface remesh surface directly means that we run the workflow that we just did before in one single shot. So we repair it and then remesh it on top of that. For those working before with TechGen, so you might remember the need to have the so-called region markers. So I can see I have a number of blocks being cut by the faults and the geological model. I would need to, in the past, create a point in each of these blocks that the FEFLOW is able to wrap all the elements and then create an elemental selection at the end of the meshing process. Now we do all this automatically. So you need to activate these, generate region markers, and we'll create a selection. So filter out surfaces is what I was referring in the presentation. So we will like to throw out all the surfaces that are outside the domain. So if I press, I should have start with the operation and explain. If I now start inserting all the different surfaces, and it's gonna come with a solution in the next minute. So in meanwhile, let's start looking the questions so we can answer. Yeah, there is a question about GenPy with PyVista. I don't know who is there. It's anonymous, but I really try to install, and I have a lot of issues with installation of GenPy. It's a very good, I mean, what I read is really good option for geological model in Python. Okay, super mesh is done. So I have seen that this has cut the different surfaces and throw away the rest. So here there are two ways how you could proceed. The option number one is you are satisfied with the outputs resulting triangulation, and then you just go forward and create the tetrahedral mesh with FEFLOW. And for this, you will go to the meshing panel, then you have TechGen, and then if the tetrahedral, if the triangulated mesh is really good, so then you can say call TechGen with the preserve external boundaries and then generate the mesh, and the mesh is done, and it has the different cuts and intersections. So that's here is doing the minimum because it's not really touching the outer faces of the domain. Here is something that you need to be aware with. The quality is good. So if I try to zoom here, because we didn't force any triangulation outside the repair, after the repair, maybe that we have some angles here not well connected. So we can always look in auxiliary data, then you have a number of parameters to control, like the condition numbers. So we can just take now randomly the aspect ratio and see, okay, yes, indeed, there are some tetrahedrals with a very high value. So maybe it was not a good idea to just do a simple mesh, tetrahedral mesh after the remesh. So we can go back, and now let us now run this, but without the preservation of external boundaries. So we can, this is going to take a little bit more time, but it's not that much. It's now done. So let me open FEFLOW. Now you see we have the additional points being added here because it's coming from the repair mesh. And if I look the aspect ratio, now it's a little bit less, it's better, but probably still not enough for what I need for my project. So I could go back again to FEFLOW and say, okay, now I leave TechGen aside and I come back to the super mesh processing, and let me call, now the mesh has been repaired, so there are no self-intersections. So let me call the remeshing process on top of this. This time I would like to preserve the original vertices, so use the sharp features option, and I have no idea about the target length, so I will just leave it at 0, and then FEFLOW will provide a good target element size, so we can read it here is using 300 meters. The process is already done, it's quite fast, the repair. So we started with 14 blocks, now we have still 14 blocks, so we have 42 surfaces because we are calling with sharp features. It needs to preserve a high number of features in order to maintain the geometrical information. So we have 8,423, and the number of vertices. So we didn't even include much vertices. We reduced slightly from the original number, from 7,000 down to 6,800. So most of the operation, which takes some time, is where we start building the super mesh. So this is something that we have improved. And in between the release A0, there was an update 2 weeks ago or 3 weeks ago, which is better, the performance, but still we want to do a lot of performance improvements. Now the mesh is done, so we can call again TechGen. So I can say this time, because the triangulation looks fine for me outside, so we can run preserving the surfaces. The mesh is ready. Open again Control-3, the 3D view, and we have now the super mesh, the final tetrahedral mesh, sorry. And what I didn't show you in the previous step, so you also got the different blocks. So I have been using these planes to cut the model as I want, so I can get the blocks. And we have all these different pieces here. You also have the different phase selection. So let me deactivate this, so we can see all the different folds being cut in. So we can, I don't know if it's easy to see because of the camera angle, but yeah, you see what I mean. The different folds are preserved here. So that is the first demonstration exercise that I wanted to show. Now we move to something more larger. It's not that complicated, but let me open the super mesh file. So I'm skipping the first part of adding the folds into the super mesh because this is something that it takes 1-2 minutes. I want to say something. So these are some regional faults. They come from Leapfrog, if I remember correctly. It's a very old data set, so many years ago. So you see the triangulation is not that good. So there are, for any reason, the fault here is quite fine, quite well refined. These ones are very coarse. So first step that I would like to do is let me clean up some of these. So for this, I'm show you that previously the workflow, preserving them. Now I would like to deactivate the sharp features and then run it with a coarse. These are regional faults, it's a large model, so don't be surprised about the target's element, target lengths for the triangles. And then we have, so you can play with this parameter and see what is the level of discretization. So I can recommend you to use something in between. So now I use 750. If I would like to have it finer, if I, let's say 50 meters, I have already lost some information because of the initial step of the surface reconstruction. So you might need to reload the project to start with the 50 meters again. But if you go coarse and uncoarse, and there is obviously, you can do it in the same project. So we have this, this has been remeshed. So let me save this, let's put it demo. And now I'm gonna add the domain. We need a box. So I have created as a HMesh file with this domain. Or you can add the rest coming from Leapfrog. And I like to combine this data because I could control, if I know the topography, I could control this. So I can see that the faults are really not fitting with the box. So we need to do something about this. And for this, we are gonna now repair it without remeshing. And I would like to discard everything that is outside the box or the domain, and then also create region markers because there are some geological zones or volumes that I would like to construct or to get. Okay, so the model has been reconstructed. Let's look at it from below. So it's doing some triangulation here. This is the fault being cutting. So we can use it now to remesh the surface. So let's now add the remesh because I would like to preserve what is the information, what is there. And then maybe I want to have it finer. Let's try it with a 0 and then remesh. And it's gone. It's already done. So it's after remeshing, you can compare always 15 blocks, 55 surfaces. Now we have 3,839 and the number of vertices. So we definitely included by a factor, I think, of 3 approx the number of vertices in the super mesh. We still don't have a mesh. And it's generating the mesh. So I think we can open now. It's probably done in the minutes. I open a few to save some time. Yeah, is it done? Is it done? Now you can see that it's a bit finer. And you can use this mesh to create a tetrahedral mesh. So I'm gonna load it because it takes like 2-3 minutes. So let me open the file. Here. And that's the final model. So we can deactivate the faces and then see the different contacts which been included in the domain. Okay, so then we have also different blocks. This. Okay, so that is the second example, and now you probably would like to see what is coming. So this is available. Everything that I showed today is available. You can download it now with FEFLOW. I have my own installation A1. So we're always actively looking for beta testers. So if you want to raise your hands, let me know. So we have a number of new things implemented in the version coming. Already we have been very active with this. So let me show you one thing. So we start with these surfaces. Remember, so I remeshed the surfaces already, and I was importing a box later to create the domain. So then the idea is, so can we do it faster? Yes. So there is the possibility to create a bounding box. So I can do now in, say, I would like to build my domain immediately. You can also add a topography on top if you want, or use a topographical surfaces and then clip it. So we can use the repair already here. You would like to create faults. So with this possibility to say, okay, let me draw this still something to fix with the visualization, but you can define your orientation angle of the fault, let's say 45 degrees, set minimum and max, and then FEFLOW is gonna build your faults, and then you can create this. I was showing you before that every time you need to do a right click and then convert to super mesh polygon. So we have changed this. There is the possibility to include a number of files in one single shot so that we do it faster, and so you avoid a lot of manual operations. And with this, I would like to close the live demonstration. I would like to thank you for participating in this webinar. So you will get, as I was mentioning before, a copy of the recording, a presentation. If you would like to know more about these scripts and all the methods that I'm using, just shoot me an email and I can share easily the script with you or explain you how this were done with PyChart or PyVistas or any other topic related to FEFLOW, of course, as well. So we have next month another topics of different FEFLOW webinars. Just join the community and you will always be able to receive all this information and the materials of these different webinars. Thank you again, and it was a pleasure talking to you and presenting all this today. Until the next time, bye.